What are we talking about today? First of all, who are you?
My name's Doron Holan. I'm the technical lead for the Kernel Mode Driver Framework, which is, if you're familiar with user mode apps, kind of the MFC equivalent for writing a device driver.
Really?
Yeah. So what really happened was over the years the driver model has evolved and changed. In Windows 2000 we tacked on plug and play and power and a bunch of instrumentation and that kind of stuff. And the more and more stuff we added, the more complicated it got. And we kind of realized that writing a device driver was really hard and took a lot of time. It took a lot of testing, and that kind of the true epiphany was is that even at Microsoft we couldn't write a driver that we continuously find problems late in the development cycle, stuff like that. So and there were so many rules and there were so many ways that things could go wrong that we really decided that we needed to concentrate that into one spot, put all the boilerplate stuff into one location, and so that somebody who wrote a driver could actually do like the things that they're trying to add to the system. Like if I had some USB, I think like a USB oscilloscope, the fact that I could concentrate on the fact of getting my data off the device versus the fact that like Windows made me do like these 20 things before I could even talk to my device.
Even if you weren't interested in them.
Yeah, you had to do it. And
let's talk about that for a second.
Sure.
Why was that the case? Like, why, if I was writing a driver that had nothing to do with power, for example, did I have to deal with that in my code? I mean, what was the thinking back then? Just give everyone all the code that needs to be written for a driver, regardless of what you're.
So part of the reasoning behind that is one, we didn't know what you needed to do. So the guys who went out and set out and did it, and there's no fault against them for this. We didn't really know the world we're creating until we created it 5 years later. Was that as a driver writer, I don't know what your power requirements are going to be, so I should just let you do it. That's actually kind of a departure from Windows 9X, where the P&P Power Manager had a default implementation, and you could kind of override it and hook into it. So yeah, it had very bizarre consequences. So what would happen is somebody would bring up a driver and they implement P&P, and like, okay, I'm done, and then standby wouldn't work. Because you'd get this nice little pop-up that would say, your keyboard has not allowed you to go to sleep. Okay. And you can't do anything about that, and it's a really bad experience. And so, and then the rules for power got really, really complicated in and of its own right. So you have a complicated system for plug and play. You had a complicated system for power, and then when you combine the two, it got even worse because the OS didn't provide any synchronization between them. There was no guarantees for a lot of stuff. So it kind of what ended up happening is you write this code that you either copied from a sample, and then you were afraid to God to breathe on it, or you decided that you were brave and you wrote it from scratch. You got it together, but the end result was the same. You got a bunch of code that you didn't really want to touch and do anything anymore, and you were afraid to God to add anything to, like add feature-wise. So what we kind of had is you would get these drivers that would do just the minimal amount possible to get up and running, and then do nothing else because anything else was could lead to regressions and everything else. And so, the biggest problem with this is if you have a bug in your driver, you blue screen, right? And that's, of course, the blue screen of death. Everybody, doesn't like those. You lose your data, whatever,
Sure.
Whatever you're working on at the time.
Happens in the kernel.
Yeah.
And therefore, the kernel decides. I mean, it's a policy decision by the kernel, right? When that problem happens, the kernel says shut everything down.
Yeah. I mean, technically, you could go forward. Now, the problem is that once the exception occurred, you don't really know what happened. Right, so the kernel doesn't know that, like, well, okay, this driver blew up, but maybe it touched some driver on the right. Like maybe it touched NTFS, maybe it corrupted NTFS's memory, and now the things that NTFS thinks are valid are gone. And so, technically, you could continue from one exception, but you could just start cascading and getting more and more and more exceptions. And so, the best policy, I know the best, the policy that was chosen is that, all right, let's stop now. Let's not corrupt anything else. Let's not lose anything else. We might lost like the last 5 seconds worth of work, but we're not going to start corrupting things on disk. We're not going to start doing like heavy, serious damage.
Cool, which is one of the great things about the work you guys have done in Vista by moving stuff up into user mode. That's different. You just kill it.
Yeah. So that's actually a corollary to KMDF is UMDF. So as a user mode driver framework, and we're two teams. We report to the same manager, and they do the same thing. And the stuff that you see in the walls, they've actually implemented in user mode. It's the same code.
Okay.
So
Cool. Well, hey, stuff on the walls. Let's talk about it. What is the Kernel Mode Driver Framework?
Okay, so this is just a small piece of it. So one of the really cool things about KMDF is that the PnP and power policy. When power policy is essentially when do I turn my device off and when do I turn my device on, which seems to be a relatively simple statement, just coming out of my mouth, but actually implementation is a real bear to get right. So what KMDF does is it implements all the default behavior for you. So what you do, you can write a KMDF driver, set up your device, do a bunch of initialization, then let it run, and KMDF does all the default behavior in it for you. So we can talk a little bit about that.
Sure.
So what KMDF does is it makes PnP and power policy into a formalized state machine. If you looked at a WDM driver, which is just a driver written before KMDF, it has a bunch of variables. I'm starting, I'm stopping, I'm powering up, I'm powering down, I've stopped, that kind of thing. So I call some of these kind of gerund states, like I'm running, I'm about to stop, I'm stopping. So there's a lot of these transitional states, so while I'm stopping, I need to make sure that I'm not processing I/O or something like that. So there's a lot of complicated stuff, lots of locks. You have to drop a lock to go do something, and things can change by the time you grab the lock. It's all really nasty and complicated.
Yes.
So what we did is we said we're going to move all that state management into the framework. And so that the driver, just we kind of have a term for it, they write straight line code. So there's very few ifs. And if there's an if and there's a failure, they just return the failure and the framework handles the error and bails out for you.
Excellent.
So this is what happens. And we'll just go through different stuff. So this is the PnP state machine. The PnP state machine will respond to PnP events from the kernel. So start, stop, your device disappeared, that kind of thing. The PnP state machine will communicate with the power policy state machine.
Ooh.
Yeah, the power policy state machine is huge. The power policy state machine, what it will do is he's the guy that answers the question, should this device turn off or should this device be turned on, and when?
Okay.
So the power policy state machine then talks to the power state machine. And the power state machine is the guy that actually turns the device on and turns the device off.
All of that for such simple operations.
Exactly.
Incredible.
It's awesome. It's awesome in its complexity. So what you see here is not only is their state machine is color coded, right? So we have a bunch of like red circles, we have green squares, we have purple lines, we have black boxes, we have blue boxes, we have gray stuff. They all serve a purpose. It's not like I just went crazy in Visio and just decided to give things color. So what we've done is formalized functionality into the diagram as well, because a standard finite state machine doesn't really indicate like the real complexity of what's going on underneath. So let's step through it.
Let's do it.
So what happens is your device gets added to the system, right? So this is your standard notation for the big black circle. We get an add device, we get into an init state. Visio has a wonderful bug where it decides every once in a while to chop off the last letter of a certain state. So this is actually init, not init.
All right. Let's fix that.
Yeah, exactly. They don't want to. So then we get a PnP start device. We process it. The lower stack completes it. We tell our driver, all right, what we want you to do is to map in your hardware. So this is like if you have memory mapped I/O, you have a USB device where you need to initialize it. This is where you configure your device. And this is where the fun starts. We send power policy start. Power policy start is the message. That moves us from there to the power policy state machine. Power policy then processes that message and goes to starting. And what it does is it starts the idle state machine, which is this guy over here.
All right.
And then what he'll do is move into the stop state. He gets an idle start. He does management, and he moves into the disabled state. But there's no interaction between the two at this point in time. So that returns, and he sends an implicit D0. An implicit D0 is a power-up operation of the power state machine that does not require an IO request packet. So the problem that we had was that there's certain PnP operations which imply to power operations. So when you get a PnP start, that implicitly says that you should power up your device. And when you get a PnP remove, it's something that you should implicitly power down your device. But the problem is that a typical power operation requires an allocation. And you need to call a power API which says, give me a power herb. And then that'll get sent to the stack. But what happens then is if you're starting and you can't allocate a power herb, well, then you can't start. So there's a forward progress issue. So what we decided is that for a PnP operation, we'll do implicit power operations in their place. And that way we can successfully start the device without having to make any more allocations.
Great.
So we get to implicit D0.
Okay.
It's that guy right there. That moves us to this guy right here. So we have the black start state here, implicit D0. Now we check to see if we're a child device or not. So you can be a bus driver and enumerate more devices on the system. So let's say we're not. So we do a bunch of callbacks, D0 entry. We move all the way up the state here, and then we decide what resting state we're going to be in. And so we're just going to be in the D0 state, and we'll hang out there. But if we see at the end of this right here, Visio also has a nice little bug of rearranging all the functions within the box. This power up should actually be at the bottom. And so what this says is power up. That moves us back here. And so we see the power up operation here. So that moves us to the new state, which is power policy started, which sends the event back to PnP, which says power policy started over here. We enable our device interfaces, people can open up our device, and we move into the resting state, which is started.
Okay.
So that was just to start your device. That's pretty awesome.
Amazing.
So what happens here is, so why did we decide to put 3 state machines versus 1 state machine? And the problem is that if we put all this complexity into 1 state machine, it would be a factorial problem. This one huge state machine would just blow up into into just so many states it would be impossible to handle. So we moved it into functional pieces. So one of the things that we did to limit ourselves is, so these red squares and, the green squares and the red circles. The reason they're color-coded is that we had a couple people reviewing the state machine who were colorblind. So we needed to distinguish these different states, not only by color but by shape.
Okay.
So what the green square means is I'm resting, and I can accept all the inputs into the state machine. A red circle means that I'm only going to accept a subset of the operations that can happen on this on the state machine. So for instance, once we move into a red, and what we accept on each state machine is different. So in this state machine, what this means is that we'll only accept power policy events once we move into a red dot state, which means that, let's say we're powering up the device and we get another PnP state operation.
Okay.
What will happen is we'll pen that operation until we can get back to a green state, and then we'll dequeue it and work.
Wow.
So for PnP, that doesn't matter as much because the PnP manager provides a bunch of serialization. But for power policy, which is the huge diagram over here, it makes a tremendous amount of sense. So this is the guy that says your device should be on, your device should be turned off. He's the one that decides that your device has been idle while it's running and it should be powered off, for instance. So he has no synchronization against PnP state. So the red circle, green square combination of blocking out events is very important here. So once, if we look at any of these states here, a red square state, a green square state means that we can accept a PnP or power operation at that point in time. But once we've committed to powering up or powering down the device, we're not going to accept the PnP operation. So if, let's say, we get to here. This is the state which is we've started, we're idle capable, which means that we can turn the device off while the machine is still running. What we do is we enable the idle timer. Let's say the idle timer runs. It tells us that it's expired. Now we move into a red dot state. Once we've committed to this, which is essentially we're going to start to power down the device, we don't accept any other PnP operation. So notice there's no red lines coming out of here, which is power policy start stop type of stuff, or a system power operation. So what this means here is that once we've decided that the machine is in F0, which is the running state, and we've decided to power down the device, we're not going to process the machine coming down to a low power state or the device being yanked out from the machine until we've fully committed it, which simplifies the life of, one, the driver writer, because then they don't have to handle the fact that, like, oh, I'm partially powered up and, like, things disappeared from underneath me. And it also helps us from an implementation point of view is that we don't have to have explosions of arrows in every single state. So what happens here is we send the power down. That'll shoot us over to the power state machine. We can the same thing kind of happens for power down as it happens for power up. We complete the power down. We tell the idle timer to knock it off. You know, there's no more reasons to continue running. And then we eventually end up here in the waiting armed state. So now, or waiting unarmed. We've idled out, and now we can handle a PNP or power operation. So the power operations in this case are the purple stuff. So all the purple lines are system state changes, and all the red lines are PNP changes. And we actually distinguish between your device disappeared, like an ungraceful remove, like you have a USB mouse and I yanked it out of the machine, versus you went to device manager and said disable, something like that. So one of the interesting things about the framework is, and especially these state machines, is that we actually thought about handling every single error case.
Nice.
So what happens is that in a driver, usually it's like, oh, that failed, like to do, I'll fix that later. But we had to, because we formalized everything, and we're putting in the driver writers putting their trust in what we wrote. We really had to be very resilient to every single type of error. So you see a lot of gray arrows coming out of here. So every single gray arrow is an error. So typically these are an error that either the system feeds back to us or the driver writer in their callback that we make a call into them is return an error to us. So like if we fail to allocate a power ERP, we will continue to let the machine run down, but then we'll hit an error state and we'll get the device removed from the system, stuff like that. So up here is the implementation in blue is my device is in low power, the machine is in low power, and my device is armed to wake up. And by armed to wake up, that means that, let's say you put your machine into standby and you move your mouse and then your machine wakes up. Right, that's not, that doesn't magically happen. Like, there's a lot of stuff that has to happen at every single layer for everybody to arm themselves for that to happen. So, and that's typically a very difficult thing to manage. And what we found is when we were telling people to write a device driver, we kind of waved our arms and said, all you have to do is arm yourself for wake. I mean, how hard could it be? And we got a lot of feedback that basically said it was, no, that's hard, right? That's really hard. So one of the two big things about the framework is in addition to doing the PNP and power stuff, is we wanted to move the platform forward. We wanted to say, all right, not only are we going to give you default implementation, we're going to do advanced implementation for you. We're going to give you the ability to aggressively turn off your device, aggressively turn it on, and to give you a lot of state changes that typically were very hard to implement, and we would do it for you. So one of the biggest hand waves that we gave people was, when your device is not in use when the machine is running, just turn it off. And then when people are using it again, turn it on. And that was actually a tremendous bear, because not only do you have to determine that you're idle, you have to figure out that nothing is coming in, and you have to, once you've determined that you're idle and you're starting to go down, anything new that comes in you have to append until you've powered down and powered up, because those are pretty much, you've committed to doing that. So there's a bunch of races, you have to start queuing stuff, you have to, there's just so much stuff that you have to do that, people looked at it and went, yeah, right. And I mean, I implemented this, I used to own the Bluetooth stack. And there was a feature where Bluetooth radios on laptops could turn themselves off to save the battery power in the machine. And I implemented some of this, and it was awful. I mean, it took weeks just to get it right. And it's not because I'm a bad engineer. I mean, I think I'm a pretty good engineer. Like, it's the fact that it's just a hard problem to solve. So we concentrate in that one spot.
Excellent.
And so that's what all the green is. The green here is dedicated, again, some more color coding, is dedicated to the functionality of turning your device off while the machine is running. And it's not trivial. I mean, you can see here that powering down and going through a bunch of stuff, and this is just a failure path, is we tried to arm ourselves, it didn't work. Let's disarm ourselves. If we're doing USB, there's some special functionality. We tell the power state machine to power down, and then we power ourselves back up. Or in a lot of these cases, depending on where we're at, there were errors, and we eventually move back to the Uber error state, which will then get the device yanked from the machine.
Okay. Now, it's again important to stress that this is the underlying framework.
Yeah.
And so basically what you've done is you've abstracted the stuff away from me, the developer. I can just concentrate on writing the stinking driver.
Yeah, and we're really big on contracts. So what happened is, let me go get a pen.
Sure, please.
Is the way we abstracted it is we said, all right, we're going to do the basic operations, and obviously you as a driver developer have to do. You still have to turn your device on. We don't know how to do that, right? Mm-hmm. We don't know how to turn on your DMA engine. We don't know how to read from your USB device. Mm-hmm. So what we did is we, one of the guys who actually came up with the state machine idea, Jake Oceans, calls it the layers in the cake. Mm. And so what we do is we say, all right. We also have a naming convention. We try to be really consistent in what we do. Right, so we have the first layer of the cake. So the power state machine says, all right, you're always going to get the zero entry first. We're then going to enable your interrupts. We're then going to give you another D0 entry after your interrupts have been enabled. My handwriting is atrocious.
It's fine, I can read
it. We're then going to start DMA. Mm-hmm. We're then going to start power managed I/O. I've talked about the distinction between power managed and not power managed I/O. And then we'll do self managed I/O. So what our guarantees are is that, and some of these are bigger sets of callbacks than just this one thing. Mm-hmm. What we've guaranteed is that this will always happen in upward order. We'll always give you D0 entry first, we'll then always enable your interrupts. We'll always, give you a passive level callback after your interrupts are enabled. We'll always then enable DMA, always then enable self-managed I/O, and then always do self-managed I/O. And this is the self-managed I/O is a great bit bucket of escape. Mm-hmm. Basically, what we've done is we formalized and said, D0 entry, you're going to do these very specific things. You're just going to turn your device on. Interrupts enabled, you're going to be very specific. You're going to enable your interrupts. The post interrupts enabled, you're going to do any processing that you need to do with your interrupts enabled. Mm-hmm. And so, you're supposed to do very specific functions at very specific times. And then, obviously, people's devices don't always fit into that. I have a timer that, every second checks the state of my device to make sure it isn't hung. Mm-hmm. Well, it doesn't fit into any of those categories. Mm-hmm. So what we've done is, we've given the self-managed I/O at the top that says, all right, go do all the things that you need to go do.
Okay.
And what that has done is he's given a very formalized structure. So instead of one function that does 20 bazillion things, we've kind of cracked it apart and said very specific things happen here, and we realize that at the end you might have to do some more stuff. So one of the interesting things here is that by the time you get to self-managed I/O, you know the rest of the state of the device. It's a guarantee to you.
Excellent.
And the same thing happens on power down, right? So the layers of the cake get pulled off. So on power down, we turn off self-managed I/O first and do all these other things. And so the great thing about it is that when I'm turning off my device or turning on my device, mm-hmm. I know that no I/O is hitting my device because power managed queues aren't on yet. So what you've seen in previous drivers is a bunch, I have to do everything under one gigantic lock, or I do a bunch of state management. It doesn't happen anymore because all the contracts that we've layered into every single part of the cake, mm-hmm. You know what's on, what's off. You don't have to synchronize against it because it's not on yet, or it's been turned off.
But I'm still going to have to write locks.
Not really.
Okay. That's a really incredibly important point.
Yeah. So we have some statistics on WHDC. There's some white papers, and if you've ever been to WinHack, we have some slides where we took the serial sample, which is that drives your COM port, right? It's a great WDM sample because it's so complex, and it's just, but it's also one of the world's worst samples because it's so complex. Mm. And what we did is we converted to KMDF. And what we saw is that the WDM version had 50 locks and 25 state variables, and the KMDF version, I think, had 4 locks and 3 state variables. Beautiful. And those only had to do with the actual hardware, versus the rest of the stuff had to do with the state of the device in terms of what the OS inflicted upon you as the device driver writer. Mm-hmm. So it really reduced the driver into its core functionality. Mm-hmm. And you see drivers that used to have 2,000, 3,000, 4,000 lines of code dedicated to PnP and power mm-hmm. have under 100. It's some seriously awesome stuff in terms of reduction of complexity and simplicity, and introduction of simplicity, so that one of the biggest things that we wanted to do was make Windows a great platform for writing drivers again. So that, let's say some company who has really low margins creating, like, our favorite example is a USB Homer doll that has a USB plug coming out the back, and all it does is it plays WAV files. And some guy had to write some driver that was crashing Windows XP because it just didn't do stuff right, and it crashed all over the place. Yeah. That guy doesn't need to spend 5 months writing a driver and creating this performance, like, awesome, piece of code. All he wants to do is basically get bits onto the device and not care about, how slow it is, as long as USB Homer can wave his arms and sing the WAV file. Yeah. So, one of our goals was to make it so that a guy could write a driver in a week and then crank it out there. And that's what this code allows them to do. Is obviously you still have to read some docs. You still have to kind of look over a sample and kind of figure out what's going on. I mean, you can still screw things up. I mean, it's kernel mode for one, sure. And two, if you don't understand the paradigm that you're running in, it won't work.
Understood. Now, one thing I would ask is that the last comment you made is interesting in the sense that there's 2 points. One, whenever you create a framework for people who typically have been pretty much rocket scientist developers.
Yeah.
Those are the kernel guys. Those are the device women.
Yeah.
Those are the people that are really writing down the metal.
Yeah.
When you give them a framework, in some sense, you're taking away a little bit of their ability to rock the metal. So that's going to be the initial feedback you're probably going to get.
Oh, we've already gotten it.
Okay.
Yeah. So, and that's one of our biggest fears, right? Is we understand is that we're introducing a layer of abstraction that things are slower. But some of the things that are slower, like for instance the PnP and Power Policy 8 machine, because it's formalized, there's a little bit more locks and stuff like that. Sometimes slower doesn't matter. Like when I'm bringing up my device, the fact that it took 500 milliseconds versus 20 milliseconds the first time I plugged it in, and those are numbers I made up. Those aren't real, right?
Sure.
Just to give a wide difference of numbers. It doesn't really matter because you're not processing. That's not the I/O path. That's not the hot path. So some of this stuff, it's okay to be a little bit slower and still be fine. And what we found is we've gotten feedback from a lot of the communities is like this PnP and Power stuff and the ability to do queuing is awesome, and that's definitely the killer. That's totally that brings people in, and they get to throw away a bunch of code, and it just works.
Excellent.
And in the end, touching the code, if you're bare to the metal, like you're touching hardware resources, you're doing DMA, the framework doesn't add a lot there. It adds a little bit of formalization in terms of when things start and when things stop. But we're not talking about you have to go through our object and go do this thing. And one of the other things that brings a really good point is the framework is we kind of call it the Great Escape. So underlying to any object that the framework encapsulates, we can give you the underlying WDM object. We can give you the empty kernel object. And we don't encourage you to do that, but we realize that one, we're not perfect. So if in case we didn't give you some piece of functionality that in the abstraction that you needed, you can go out to get to the underlying request and go get it. So for instance, the framework handles reads, writes, I/O controls, internal I/O controls in part of its queuing mechanism. But let's say, and the serial example is a great example of this, there's an ERP that's flush buffers. So we're not going to add a whole layer of abstraction to the framework just for this one sample to get it working. So they can install an I/O filter that basically sits right before the framework and is formalized within the framework. They say, okay, give me flush buffers. Give it to me in this callback over here, and I'm good to go. So we've given them the ability to work around the framework. One of the biggest distinctions, if you think of the in kernel mode, a really big popular pattern is called a port-MiniPort model. So you have this big encapsulating driver, like a SCSI port, which does for SCSI controllers. And it creates this environment for you, similar to the framework. And you just have to write a very specific piece of code that gets it working. The problem with those models has been, and continues to be, is that they were very restrictive. They basically say, you only can call me. You can't call out into the kernel. You only can play in the little bubble that I gave you. And what happens is you start seeing people getting very frustrated with that situation because they want to innovate. They want to do some things outside the bubble, but due to various reasons, the assumptions made, it doesn't work. It's very difficult. Things crash. It's unreliable. That kind of stuff. So in the framework, we kind of took the opposite approach. We said we're going to give you this nice fuzzy circle, but we're going to let you break through. Excellent. We're going to let you pop through and do whatever you want it to do.
And so, then, of course, the other question was. And this is, pretty much based on my misunderstanding.
Fair enough.
Is if you build a framework, why can't you have more control over the exceptions that may occur? And I mean, and you do in that map, you know the exceptions happening. So instead of like blue screening the machine, you somehow know what device is having the problem, and you just turn it off. So I know that's kind of that's a novice question. I'm not a kernel developer.
So part of the problem is that where the exception occurs in the kernel, right? So let's say I'm touching a bad piece of memory. I don't know, like the framework calls into, let's say, EVT device D0 entry, right? Go power on your device, and it goes up and touches bad memory. It doesn't come back to the framework. It goes off into the kernel, and the kernel handles the exception, and then things start to tear down from there. On the other hand, though, what the framework does is when a bug check occurs, right, the blue screen of death, the framework registers a callback, and in that callback, if we can determine that your driver was the one that blew up, and we can't do that for a lot of them for various reasons, but if the bug check code has a function address or something like that, and we determine that it's you, we start scribbling stuff to the mini dump that says, hey, this is the last 100 things that the driver did in our log, so that when you get the mini dump, it might be able to diagnose what the driver did and do that kind of stuff. But bringing back to the other point, if we knew what the driver did wrong, we could backtrack and undo the state. And actually, there's a couple of teams that that's an idea that they have is what happens if we knew what was going on exactly? Could we roll back the driver? And we have some of that already in terms of if you return let's say you don't totally hose your system, but you return failure. We know enough in the framework to be able to tear down your device and bring it and to tear it down and to stop it. So we kind of have a little bit of software resilience. But if you're doing something that's going to result in a blue screen, the framework is yet another driver. We're not anything magical. We're actually written completely with publicly documented APIs. We're not doing anything that's out of the ordinary or reaching into the guts of the kernel. Partially because we run on Windows 2000, Windows XP, Server 2003, and Vista. Wow. So that's part of the value add is that if it's only in Vista, people won't adopt it, right? For somebody to really make their life easier, really has to be a good sell for them. So we go all the way back. Excellent. So in terms of Star Trek-y future kind of stuff, and I mean we're not making any promises or anything like that. I mean, could you see a time where in kernel mode things would be running maybe inside of a virtual machine where the stuff is being handled, and then it would be easier just to kill the machine? You could be running as a completely separate VM, and then you could be running it in a whole variety of encapsulation methods. Right? There's a bunch of research going on, publicly in universities that talk about tracking how people touch addresses and if it's valid, and how to track back and that kind of stuff. Cool. One of the cool things about isolation, which is really what you're talking about, right, is how can I separate this thing away from everybody else so if it dies, I know that it didn't touch anything else, right, and I can just blow it away and know that the rest of my system is secure, right? That's really what you're driving at, is that WDM exposed a bunch of data structures and everything else that we didn't know if they manipulated or not. The framework abstracts everything away in terms of handles and in terms of callbacks and these other things. So you can't manipulate directly the state of a framework object because you just basically have a cookie. So the framework brings it to be the realm from highly improbable to way more possible, because we now have the right abstractions in place to be able to in the future decide at some point in time, hey, this might be a cool thing to do. We can we can take the source code, recompile it, and provide framework abstractions in some other environment and do something that way. Fantastic. Now, how do driver developers communicate with you? Do you have a blog? Yeah, so I have a blog. It's blogs, msdn.com/Doron.
Okay, we'll put that on the post.
Yeah. All right. It's called A Hole in My Head.
Excellent.
It's kind of a play on my last name.
All right. Interesting.
And I personally am really active on in the community news groups, so Microsoft Public Driver Development and NTDev, which is an OSR.com mailing list. Okay. So I'm pretty vocal in the community. Also, a coworker of mine, Elias Haku, is also really vocal, and we take feedback and we put it in the framework. I mean, there was something that was reported 3 months ago that the framework wasn't freeing a middle chain off of some I/O, and we looked at it, and yep, sure enough, we didn't know about that one quirky rule, so we fixed it, and it was in the next version of the framework. So we really believe in community feedback. And not having a wall between us and our consumers. I mean, that's really important for us, because if we build it and it's completely unimportant or completely irrelevant to the people we're building it for, we haven't done our job. So relevance is very key for us.
Very cool. Now, so a little bit about you. How long have you been working at Microsoft? You've always been in kernel world?
Yeah, so I've been here 9 years. I've always been writing drivers straight out of school. It was when I got hired, I had a choice between working at the time for Lou Perizzoli, who was the guy who owned MM and the NT4 and Windows 2000 days.
MM being memory manager.
The memory manager. He had all the driver guys reporting to him. It was between that and working for the Java guys. When Microsoft still supported Java. And so I actually was debating it for a while, and then a friend of mine at school slapped me upside the head and said, "Don't you see the writing on the wall? You know, the operating system guys are going to be there forever. Java can disappear in a day." And so and then when I started here, I owned the PS2 driver. So your PS2 keyboard and mouse, which is one of the world's worst drivers, partially because I wrote it and that's how I learned how to write a device driver, but also the hardware. There's a joke between me and the guys that actually do, you know, all the like the touchpad stuff on your laptops, that it was written by some college intern in 1981 in Boca Raton, right? the entire interface. And so after I did input, I had like gaming stuff, like so your game controller, stuff like that. I worked on Bluetooth, and I was the core developer on Bluetooth. Excellent. And did a bunch of the core architecture for that. And then I moved over to the framework. So cool. Been a driver guy forever, at least in terms of my professional life. So how do you feel about more and more kernels migrating up into user mode? Kernels or drivers? Oh, I'm sorry, drivers. Yeah. That's way in the future. Yeah, sorry. I mean, it's certainly. I think in terms of people wanting a stable machine, if you treat your PC as an appliance, you certainly want to be able to put them out there. And like, I'm not worried about obsolescence. I mean, in terms of my job, there's certainly, even if it's in user mode, there has to be something in kernel mode that reflects it back up and does that work. Sure. But in terms of, you know, my mom and my dad plugging in a device, you know, you want to get rid of the fear of like, oh my God, what's going to happen, right? Like, is this gonna screw with my machine? Is this gonna crash my machine? Like, you want to get rid of that fear. And so I think it's awesome if we can move everything up there. And it's also an interesting thing is that for writing a driver, there isn't a bunch of tools out there like Visual Studio, right? We don't have Visual Studio integration. Why not? For a variety of reasons. Okay. We can't, sure. Say it before it's hard. I don't want to get into that. That's fine. Yeah. But if you write a user mode driver, you do have those tools, right? You do have all that stuff out there. And also, you know, we see more and more people coming out of school who aren't doing C, who aren't doing C++, who are doing, you know, managed code, who are doing all these, you know, higher level abstractions, and, you know, getting somebody into Microsoft or another company, finding a guy that can do kernel mode code is expensive. So from our ecosystem point of view, we want people to innovate. We want, you know, other companies to be able to write drivers and be able to hire people who can write them. So moving into user mode is I think very key for that. So I mean, for most people, the driver development is really a black art. Yeah. And when you talk about innovation, I mean, what's an example of innovation inside of a driver? I mean, you're interacting with a piece of hardware, you're dealing with interrupts, you're dealing with, I mean, let's talk about that for a second. So we want to get, so like with .NET, right? Yeah. With the whole managed world. The great thing about the managed world is that as a developer way up in user mode, you get to concentrate on algorithms to solve various problems, business problems, UI, that kind of stuff. And the framework actually, we see drivers now, that's what happens. Like 99% of the code is focusing on how to interact with their device and the algorithms that they want to use, and, you know, whatever their spec says they need to talk with the device, versus all the GORP that the OS required you to bring the device up. Cool. So it's a similar concept. Yeah, and it's, you know, we looked at the framework guy at the C# CLR stuff, and we patterned some of our stuff after that. Obviously, we don't have managed code, we don't have like a garbage collector, but we try to be consistent with our naming. We try to present patterns and kind of like intuitive discovery, like, oh, this was named this. Well, like, oh, that other thing is also kind of like, it uses the same. We use the same verbs. For instance, like if you want to retrieve a property that can't fail, it's always get. If you can want to retrieve a property that will fail, it's retrieve, right? So set is the opposite, is an unfailable assignment. Assign is a failable assignment. So one of the things that leads you to is a set call is void, versus an assign call will always return empty status. So we try to do the same type of intuitive leaps of ahas, right? So you hit one layer of okay, I just need to get a driver running, and then all of a sudden okay, I need to get to the next step where I need to add this other piece of functionality, and so you can kind of well, the patterns are the same, so I can find it.
Excellent.
And stuff like that. So we have one thing where it was called grep by directory. One of the original developers wanted everything named so that one of the naming patterns in the kernel is the subsystem, so like IO operation object, so like IO set, KE set event or KE clear event. Well, the problem is how do I find everything that has to do with an event? I have to search for KE, pipe that through another grep that searches on event, and kind of see what's going on there. But for the framework, what we did is we said everything starts with WDF object operation. So all I have to search for is, let's say, is WDF device, and do a find stir in the headers, and you'll get every single function for it automatically without having to do any harder work. Not through piping the results of one grep to another is hard, but we try to make it as easy as possible.
Excellent. So in other words, you have a new improved API.
Yeah.
Right. That's more. It's more like the BCL.
Yeah. Exactly.
Right.
Yeah.
Conforms to that sort of, because the BCL is a pretty nice piece of.
And one of the dev lead for the previous versions of the framework was actually, he's really into the BCL and rotor and into trying to do different things with the C# framework, or the BCL, and to do that kind of thing. And he took a lot of those ideas and implemented them in the framework.
Beautiful.
So. Well,
that's great to see. Well, again, do you see a time when we'll have managed kernel drivers?
Managed kernel, I don't know.
Sure.
It's certainly feasible. It would not be the managed code that you would think of as C#
Absolutely.
or the CLR, right? It would be a very cut down kind of thing. But a managed C# user mode driver, why not? Right?
Sure.
Because the framework provides the right abstractions for that, and we can build our own, framework on top of that and let it go.
Outstanding.
I mean, it'd be cool.
Well, this is really great stuff, and thank you for your time. I mean, I think driver developers and kernel mode are going to be psyched with this.
Yeah.
And on the post on Channel 9, we'll have a link, I'm assuming, to the bits.
Yeah.
A link to
we have
your white papers.
Bits. Yeah.
And how about a link to these images?
The images are
internal only for now.
Yeah, I'd love to give them out. The issue is that one is people look at it and go, look at the morass that Microsoft created. They created the system of oh my God, what's going on? That's part of it. And the other part of it is you kind of need a walkthrough for them, right?
Right.
Not that you need me, but you need somebody who knows what's going on to say, this is how it starts, this is how it ends, this is how it travels in the middle. Because otherwise you just kind of look at it and go, oh my dear God.
Well, I have an idea maybe for a screencast on Channel 9 where someone on your team could basically the developer is just simply looking at that image while you're talking through it.
Okay.
Could be helpful.
That would be awesome.
But
I'd have to talk.
We can make that happen for you.
We'd have to talk up the layers just to make sure that that's kosher.
But hey, thank you so much for your time. Great to meet you.
No problem.
It's always fun to talk to kernel people.
Cool.
Take care.
Thanks.